Welcome to our channel for probability and statistics. In this video, we will introduce and explain briefly the notion of probability of type 1 and type 2 error in hypothesis testing. So we know in hypothesis testing, we can get two results. One is the rejection of null hypothesis, and another result is we just hold this null hypothesis. So null hypothesis is H0, and alternative or rejection of the null hypothesis is to hold the alternative hypothesis, which is called H1, right? So there are usually two types of error we can make. One is the rejection of the null hypothesis, but actually the null hypothesis is true. So we make an error in this situation. This is called type 1 error. So for instance, the new vaccine may be no better than the one now in use. And the one now in use is H0 is true. So in this particular randomly selected group of individuals, if we get more than 8 surpass the 2-year period without contracting the virus, so we would be committing an error by rejecting H0 in favor of H1, when in fact H0 is true. So this is called type 1 error. And the second error is the non-rejection of null hypothesis. But actually, the null hypothesis is false. So this is called a type 2 error. So for example, if we get 8 or fewer of the group surpass the 2-year period successfully, and we are unable to conclude that the new vaccine is better, and when actually the new vaccine is better. So actually H1 is true, but we failed to reject the H0 and we hold the H0 alternative. So in this case, we fail to reject H0 when in fact H0 is false. So this kind of error is called a type 2 error. So this table shows the possible situation when we commit a statistical hypothesis testing. So usually there are 4 possible situations that determine whether our decision is correct or in error, based on the H0 is true or H0 is false, and based on action we reject H0 or we do not reject H0. So if H0 is true, we do not reject H0, so this is a correct decision. And alternatively, if H0 is false and we reject H0, this is also the correct decision. But the other two situations where H0 is false, but we do not reject H0, though we make a type 2 error. And alternatively, if H0 is true, but we reject H0, then we make a type 1 error. Now we take a look at an example to explain and calculate the type 1 error. So the probability of conducting a type 1 error, also called the level of significance. So we denote this is alpha. So in our illustration, a type 1 error will occur when more than 8 individuals inoculated with the new vaccine surpass the 2-year period without contracting the virus, and the researchers conclude that the new vaccine is better, but when actually equivalent to the one in use. So when actually the H0 is true, but we get the conclusion will in favor of H1. So we will think new vaccine is better, but actually it is not. So this problem, if we calculate the alpha level or the type 1 error or the level of significance, they are the same thing. We can use the binomial distribution, because each trial we can get the real one is about 1 of 4. So this is the H0, and actually H0 is true. So we based on this is true. Then we can get a random sample larger than 8 positive. So we calculate this probability, then check the table of a binomial distribution. We can get about 0.0409 for the alpha, or for the level of significance or type 1 error. So you can see when the null hypothesis P is 1 of 4 is being tested at the alpha 0.04 level of significance. So sometimes the level of significance is also called size of the test. Or say the critical region is 0.0409. This is the same thing. It's very small in this example. So which means it is unlikely that a type 1 error will be committed. So consequently, it would be most unusual for more than 8 individuals to remain immune to virus for a 2-year period using a new vaccine that is essentially equivalent to the one now on the market. What does this mean? It means we just hope alpha is as small as possible. So usually, if the alpha is less than 0.05, then we will reject the null hypothesis. Because this is quite unlikely events, unlikely situation, but it occurs. So if the null hypothesis is true, then we get the 8 positive. If the P is 1 of 4, but we get 8 positive from the 20 random samples, this probability is quite low. Then we reject the null hypothesis because the very unlikely event occurred. Then we reject the null hypothesis, but on the basis we have the possibility to make an error if the null hypothesis is true. But this error is quite low. This is the same as this alpha level. So we reject it, but we cannot omit that we do not make an error. We cannot say we always 100% right. So we have the probability of 0.04 to make an error in this situation. So this is the significance level or size of the test, or type 1 error, or the critical region. This is same thing, is alpha, right? So we hope this alpha is as small as possible. In most hypothesis testing, we just take 0.05 is the critical level. If we're less than 0.05, then we reject it. Otherwise, we do not reject it. Now we take a look at an example for a type 2 error. So the probability of committing a type 2 error, we know the beta. The type 2 error usually use the beta in statistics in hypothesis testing. But it is impossible to compute beta based on H0 only. We must have alternative hypothesis. Then we can calculate the beta. Why? Because we want to calculate what's the probability we can make, what's the probability of the error we can make, that we do not reject the null hypothesis, but actually the H1 is true. So in this problem, we have to specify the H1 level. So if we want to calculate the type 2 error, it's quite different from when we calculate the type 1 error. In calculating the type 1 error, we only know the information of H0 is enough. So we can calculate the type 1 error based on the random sample we can get. But if we want to calculate the type 2 error, we have to know the H1 level, alternative hypothesis, which means if the alternative hypothesis is true, then what's the probability of not rejecting H0? So this is the calculation of type 2 error. So in the example of we obtaining 8 or fewer positive in the group that surpass the 2-year period, when actually the probability of success rate is 1 of 2. So in this case, we also use binomial distributions table. So the type 2 error is the probability of x less than equal to 8 when the real probability is 1 of 2. So the result is about 0.25. So you can see the 0.25 is quite high probability, indicating a test procedure in which it is quite likely that we should reject the new vaccine when in fact it is superior to what is now in use. And we like to use a testing procedure for which the type 1 and the type 2 both small. And of course, we cannot get both error to 0. We will not go into detail here, but it's not possible to get both very, very small. If we, in this example, set the real or alternative p is 0.7, if we calculate it again when x less than 8 from a 20 random sample, then the beta is quite low. So this is the ideal size. So with such small probability of committing type 2 error, it's extremely unlikely that the new vaccine would be rejected when it was 70% effective after a 2-year period. And actually, if the alternative hypothesis approach unity, so we say if the p equals 1, then the beta will equal to 0. So it's very, very unlikely that you will not reject the H0. Thanks for watching.